What do you mean intuitively here? I have added the sum of all distances from the mean and divided by the total number of these distances. If I add n quantities and divide by n, what do I get? An average. So this is also an average. This is the average distance of an observation from the mean. Right? This is the average distance of an observation from the mean. This is called the variance of x. Yeah? This is called the variance of x. The average distance of an observation from the mean. Right?
How can you call it an average when
because
you're
when
comparing it?
Yeah, but I said, what is this? This is a distance of x1 from x bar. My idea of a distance is x1 minus x bar square. So this number tells me what is the distance of x1 from x bar. This whole thing tells me what is the distance of x2 from x bar. This thing tells me what is the distance of x3 from x bar. So if I add all these distances up, the numerator gives me this total distance of all the 5 observations from x bar. If I add this and then divide by 5, that will give me the average distance of all observations from x bar. Right? Going by the rule that if I add any n quantities and divide that sum by n, I get an average. Right? So this is called the average distance of an observation from the mean. It's called the variance.
What is deviation in practice? Deviation.
What deviation?
So what is deviation like?
Standard deviation.
Right.
The standard deviation is nothing but the square root of it. You know, I will get a square root because I need to square, no, to keep that additive property correctly, right? So if you take the square root, you get the standard deviation, right? So but first let's understand the intuitive meaning of this. So what is the variance of a set? So if I tell you that there are these 50 observations and their variance is 6. Their variance is 6. What does that tell? There is 50 observations and their variance is 6. What does it mean? What does
Average distance all around different.
of average distance? That is, or in other words, if I pick up one of the numbers randomly, then and if I kept on doing this and measuring this distance from the mean, then on an average, that value will be equal to 6. Right? It says that is a collection of numbers. If I told you that the average distance of an observation from the mean is 6, it means that if I have to pick up a number randomly, pick up an observation randomly, subtract that observation from the mean and square, and record whatever quantity I get. If I kept on doing this, I get many such quantities. The average of those quantities will be 6. That is, on an average, if I randomly pick up an observation, then I will get 6 as the distance of that observation from the mean if I am using this one. Okay, tell me one thing. Why does it have to be always the mean? Why have we chosen x bar? I could in principle think of any number x, no, and calculate the distance. No. Can you give from the context of what you've learned? Forget all the statistics that you have learned in the past. We are starting with a very completely clean slate, right? So let's not have any cobwebs.
We need to have some common reference.
Why is x bar chosen as the common reference and not any other number?
The expected value we want to find out.
Because x bar is the property, it minimizes the total distance from the mean. So therefore x bar is a benchmark. You know, when you calculate xi minus x bar square, I could actually have said, if I got numbers 1, 2, 3, 4, I could actually have said x1 minus x5, you know, x5, and I could have got some average. But that would not have made sense, because then if you chose, say, x2, it would be another. You would never get any correct idea of what the number is, right? And therefore, we choose x bar because x bar minimizes the sum of, we choose it as a benchmark because it minimizes the sum of all the deviations from the mean, right? Is that clear? Sure. So what x bar means and what variance means? So variance is a different average. It's a different average. Okay? It's a different average. But it's an average of squared deviations from the mean. So it's not different from x bar in its analytical construct. Right? So very often we are told measures of central tendency and measures of variance in the introductory textbooks of statistics, they should not be dealt with separately. Right? The basic idea is the same. And it's very important really to look at the variance also as an average. I'll tell you why. Suppose I ask you, suppose say there is some average per capita income in Mumbai in the real exercise, but does everybody have the same earning, or do people have different earnings and the average is the average of all of them? So the average is say 10,000 rupees. Then there will be some people who earn a lot more than 10,000 rupees, some people who earn a lot less than 10,000 rupees, right? So if I ask you, if I take a person at random from the Mumbai population, what would generally be the difference between that person's earnings and the average earnings? Then you ask a question about the variance of the whole population. Yeah, you ask a question about the variance of the whole population. That is, what would be the difference between the mean earnings, the average earning of a Mumbaiker, and the actual earning of a randomly picked up Mumbai. Then you ask me a question, what is the variance of the entire population? And if you have to calculate that, can you ever calculate that variance? No, because you have to go to each individual, find out what his income is, find out then get the population income, then each income minus the population income, square, sum, divide by some 1.5 crore or something, and you will get that number, right? But you can't ever get that number. So how will you achieve that number? You'll take a sample, right? Now, if you look at the variance of the sample mean, the large number tells you that the sample size increases, the sample variance will also get closer and closer to the population variance because both are averages. Yes, so it also tells you that the sample variance will also be a consistent estimate of the population variance because both are nothing but averages. And any average based on a sample, as the sample size gets bigger and bigger and bigger, gets closer and closer and closer to the population average, the corresponding population quantity. Is this clear? Right? Therefore, the law of large numbers comes into play again. It says the sample variance will also be getting closer and closer to the population variance as long as the sample selection is random. If you are selecting the same people over and over again, then you'll obviously, just because the information increases, you'll never get that picture. Like if I wanted to get say an image of how say Chhatrapati Shivaji would have looked like when he was at home, right, having dinner or something, right? Okay, now I can't actually go and see how Chhatrapati Shivaji looked at it. All that I can do is I can see pictures and portraits and and obviously if I have lots of portraits of Chhatrapati Shivaji having dinner, and if I kept on looking at more and more of them, then I would get a clearer and clearer idea of how Chhatrapati Shivaji was looking at, look when he was having dinner. But suppose I don't have any of the photographs of Chhatrapati Shivaji or statues of Chhatrapati Shivaji ever having dinner, right? All the photos I have are, all the statues I have of Chhatrapati Shivaji riding on the horse with his sword drawn, right? Then just because I look at more and more statues and more pictures, I would never get a clearer and clearer idea of how Chhatrapati Shivaji actually looked like when you are sitting down for dinner. Because I don't have that information. What I am doing is I am having a biased selection. Right? So only when I get a random selection, right, of different photos taken from different angles and so on and so forth, that I'll be able to get a clearer and clearer idea of how Chhatrapati Shivaji actually looked like when you're sitting down for dinner. Right? Okay, so clearly, as long as the sample is random, as the sample size increases, the population sample averages will get closer and closer to the population variance. Right? The sample variance will get closer and closer to the population variance. Is that clear to everybody? Absolutely. Right? Okay. Finally, let me now test your minds. Okay? So now, think of what I do. I have done summation xi minus x bar square upon n. Right? That's the formula for the variance. If I'm going too fast, please tell me. Right? This can be written as summation xi minus x bar. Yeah, because square. Now, suppose instead of xi, one of the xi I change to say yi minus y. Yeah? So instead of just having one x, I have say x and y. And instead of using x1 minus x bar into x1 minus x bar plus x2 minus x bar into x2 minus x bar plus x3 minus x bar into x3 minus x bar, I use the formula. So I have this, for example. Okay, say x1, 1, 2, 3. This is 4, 5, 6. Okay. So what is x bar here? 2. So I create a column x minus x bar, y minus y bar. Right? I write it 1 minus 2 is minus 1, 2 minus 2 is 0, 3 minus 2 is 1. As you see, the sum of the deviations will be 0, minus 1, 0, 1. Here what is the average? 5. 4 minus 5 is minus 1, 5 minus 5 is 0, 6 minus 5 is plus 1. Suppose I do this. And now, I multiply this into this. So what do I get? I get plus 1, 0, plus 1, right? And now I sum all these two and divide by 3. I get a number 2 by 3. What do you think this number 2 by 3 indicates for you? Intuitively again. Yeah, but what do you mean by that? It's called covariance, I know. What do you mean by that? Yeah?
How did you get to, is that, you took an absolute number?
I multiplied this into this.
So you might,
I multiplied x minus x bar into y minus y bar. This into this. So I got plus 1, plus 1. I added them. So first, you must understand these are average. Because there are 3 numbers, I've added 3 numbers and divided by 3. So it's an average. Right? When I add a certain set of numbers and divide that sum by the total of how many numbers there are, then I get an average. That's the fundamental insight. Right? So 2 by 3 is an average. Yeah? 2 by 3 is an average. What is it an average of? It's an average of something, no? Like summation xi minus x bar square upon n was the average distance of an observation from the mean. Right? So what do you think 2 by 3 is?
Average distance of mean of x from mean of y.
Is right. But can you put it a little bit more carefully? See, x1 minus x bar is the deviation of x from its mean. When will that be positive? When x is above x1. X1. When will that be negative? When x1 is below x1. Okay. When will x1 minus x bar into y1 minus y bar be negative? When will x1 minus x bar into y1 minus y bar be negative? If one of the quantities is positive, one of the quantities is negative. So either x1 is above x bar or y1 is below y bar or vice versa. y1 is above y bar or x1 is below x bar. Now this quantity will be negative if predominantly most quantities in the numerator are negative. So if this average quantity is negative, if predominantly many of the quantities in the numerator are negative, what does this mean? It must mean that by and large, when x is above x bar, y must be below y bar, or whenever y is above y bar, x must be below x bar. Which means that by and large, x and y move in opposite directions relative to their means. Yeah? Whereas if this quantity is positive, what would it mean? Same direction. By and large, if x is above x bar, y also moves above y bar. Right? And if this is 0, then there is no particular direction in which they move. This quantity is called covariance. Why the term variance? Because actually if I instead of yi minus y bar, if I just replace this by xi minus x bar, I will get xi minus x bar square, I will get the variance. right? So my formula is this is my formula, right? Okay. So instead of y minus y bar, if I again write it xi minus x bar, I get this formula, right? Sure. So really the variance and the covariance is not different things; they're the same thing, and they're not very different from the mean. All of them are means. All of them are averages, but the average of different quantities. Okay, this is very important because you see, suppose you want to find out, suppose X is a person's income and Y is that person's expenditure on education. Suppose you want to understand for the whole city of Mumbai, what is the relationship between a person's income and a person's expenditure on education. So you have to calculate this number for the whole of the city. You can't ever calculate that. All that you can do is a sample. Each sample will get a different number. But because this is an average, and that quantity that you're looking for is also an average, the law of large numbers says that as the sample size becomes larger and larger and larger, the value that you will get from your sample will become closer and closer and closer to the population value. Yeah? Will get closer and closer and closer to population. So again the law of large numbers comes into play. Right? So what we have in the sample, if you do this on a sample and calculate the covariance, it's called the covariance, right? Which is an estimate of the actual real life covariance. The real life covariance can never be known, it can only be estimated. What you get is an estimate. If you create the sample variance, it's an estimate of the population variance. If you get the sample mean, it's an estimate of the population mean. And the law of large number says that as n becomes larger and larger and larger, right? Okay, the covariance, the variance, the sample mean of the sample will get closer and closer to the corresponding population quantities. Right? That's why the law of large numbers is a key idea for all of us. Right? It says sample means will get closer and closer to the relevant population quantities. Sure? Just to check out whether you followed this well, right? Let me give you an answer. Just give you again, I'll go back to my favorite example, right? Of my schoolmaster and all that. Let's suppose today evening you get a call from your old school teacher, right? Okay, and he says, how do you do? And you say, fine, and nice of you to call after so many years. And says, no, I've become the headmaster of the school now. When he joined the school, I left school at the joint school, but now I'm the headmaster. And I've just heard that you're doing this data science course, so I want you to help me. Okay. So you ask your principal, what way can I help you? Right? He says, no, you see, we have a problem in school. So you ask him, what is the problem? He says, see, you know that, our school always tries to give the best to its students, but we never managed to do that. So yes, I know that very well. So what should we do? So he says, no, you see, the current problem is, all teachers want to institute programs which they believe are good for students. All teachers. But the problem is, what different groups of teachers believe is good for students doesn't match with each other. Right? So all of them believe that different things should be done. And because all of them believe that different things should be done, we can't do anything because unless there is consensus, I can't act. So he says, what's the problem? So he says, you see, the problem is as follows. There's a group of teachers who believes that students have selective skills, So some kids who are good at mathematics and physics, but they are not so good at literature, right? And those students who are very good at literature are not so good at maths and stats. They're below average in maths and stats. So that group of teachers is saying that look here, there are kids who want to do maths, don't make them study Shakespeare and all that. Give them some basic English, let them concentrate on maths and physics. The other group of and whereas students who are very good at literature, we don't really need to teach them complex maths, calculus, whatever. Give them some basic arithmetic, but let them concentrate on what they're good at. This another group of teachers who says that that's all nonsense. Kids who are brighter than average are better at maths and literature, and students who are below average are generally bad at both the subjects, below average at both the subjects. So the idea is let's identify students who are below average, teach them additionally maths and literature and bring them up on par with others so that the overall standard in the class will improve. And the third group teacher says that these are not newbies, we have been teaching it for many years and we know for sure that there is no relationship between these two qualities. Some kids can be good on both, some kids can be bad on both, some kids can be good on one and bad on another. So you really don't have any kind of an association. And because all these three groups of teachers are equally powerful, he says I can't do anything. So please come and help me, is what your principal says. So what will you do? How will you go about it? What do you think ought to be done? Now we have learned something, no? So use those two. That's how data science is. It's about thinking about data. It's not using ready-made formulae to analyze data. You can't. Unfortunately, we teach statistics too badly in this country. We first learn formulae and then try to apply them. Because the textbooks are bad. I don't know what the ancient Gupta Empire did for the country, but the current Gupta Empire in statistics, which produces all those fat tomes of formulae, which don't really teach you any statistics, right? So please tell me how will you use this idea? Just think through the problem.
So just to rephrase your question, you're saying there are three groups.
Yeah.
One group is where believes that both literature and maths students are good, they are supposed to be in one group, they should be taught both. And the second group says that if they are below par, then they should be combined in one group.
No, one group of teachers believes that some kids, those kids who are above average in maths are necessarily below average in literature.
They're not.
They're necessarily below average in literature because maths and literature takes different skills. Whereas kids who are good at poetry will necessarily, above average in poetry will necessarily be below average in maths. With another group of teachers who believes that those students who are above par in general are above par in both the subjects. Students who are below par in both the subjects. Whereas the third group of teachers says that both these associations don't hold. There is no particular relationship. You have to answer which one of these is correct so that the principal can start the program. Because there are three policy decisions that we have to take. At least two policy decisions that we have to take. So you must find out how you use data.
There's a set of marks of all the students in maths, stats, marks in literature,
And
their total marks. That's average that we
so we just learned the concept, no?
Correlation.
Covariance is what we have learned. This is not got as far as correlation. We just got covariance, right? What does the covariance tell you? So what will you do? You have the marks of students in maths and suppose the marks of students in literature, and if you actually calculate the covariance between them and if you find the covariance to be negative, what does it mean? Those who are good at maths who are better than average at maths are below average in literature. Those who are above average in literature are below average in maths. If you find the covariance to be positive, what do you mean? They are above, students who are above average in maths are also above average in literature. Students who are below average in maths are also below average in literature. And you find that covariance to be zero? No relation. So suppose you decide to use this idea. You are very happy, you say, "Ek lecture mein seek liya, so I can now do something good for my school." So this data set must be a really powerful thing, right? So you go home and you go to your school, you tell your principal, it's very easy to solve this, right? So you do this, you write this, X are the marks in maths, Y are the marks in literature. You go and say, I want to get it quickly done with, so you call some 5 students. You're calling 5 students because you want to just do it in class, so that average are easy to calculate. And you give them a small 10 mark test, right? And say, these are the marks. Yeah? Marks in, say, maths. Right? They are the marks. Right? Now, as well, looking at the series, it's hard to see any specific relationship. Okay. So we find the correlation. So we will do x minus x bar, y minus 1. Right? So what is x bar? Because this is adding to 26. This is okay? 5. So let's keep it simple. So 6 minus 5 is 1. 7 minus 5 is 2. 3. Minus 2, minus 1. Right? Are these summing up to 0? They are. Because they have mathematically proved that the sum of deviations from the mean has to be 0. Right? They will, you know. So just check whether they are always 0. If they are not 0, then you can be sure that you have made some calculation this thing. What is y bar? 5. 5. Right? So 2, 1, minus 3, 0. Right? Okay? Now you must multiply the two. Right? Yeah? So what do you get here?
2.
Yeah? Then what should you do? Add all of them. So what is summation? How do you get 4 minus 9? Minus 5. Upon 5. The answer is minus 1. Right? The answer is minus 1. So you find that the covariances are negative. The covariance is negative. So what do you tell your school principal? So how do you interpret this minus 1?
Except that it's second set of teachers who say teach those who are good in maths, give them basic.
So it says that it generally supports the idea that students who are above average in maths are below average in literature, and students who are above average in literature are below average in maths.